one we have to know is you're given a reaction, which is described to be an electrophilic addition, or more specifically oxidation, and that you have an alkene, which yields you two hydroxyl groups being added across a pi bond. Furthermore, it asks you to identify which of the following, after reacting with osmium tetroxide, which gives you a syndiol, would give you a 0 degree value for the polarimeter, right? Which would be the case whenever you have an achiral compound, or a meso compound, or a compound that doesn't have a chiral center. And so notice that there's another scenario where you could have 0 degrees for the polarimeter, which would be another way to say something is optically inactive, or 0 optical activity. If you have a racemic mixture, and that's not necessarily just from SN1 reactions, right? Because if you have a nucleophilic addition to a carbonyl with a prochiral center, where it can attack both the re phase and the psi phase of the carbonyl, it's possible to have enantiomers. And so in any case, whenever you're asked, which is a common type of question on these exams, anything regarding having a 0 optical activity, you know what you're looking for is an achiral compound, or whichever reaction gives you an achiral compound, be it a meso, or a reaction that gives you achiral compounds, but, chiral compounds, but in 1-to-1 ratios relevant to one another, as is the case for enantiomers. So notice that one, although it doesn't react with osmium tetroxide, because it has no reaction, it's going to have a 0 degree reading for the polarimeter based on the fact that it's achiral prior to the reaction taking place. Point being, if you have an achiral compound being treated with a reactant that it's not reactive with, then the reactant is going to be the same as the product. And because the reactant is achiral, that means that the product is also as a result. 2-isopropyl 4-hydroxy cyclohexanone. If you have cyclohexanone, one thing to know is that this is perhaps the only time in nomenclature where we can say the ketone is going to have the locant having or being carbon number 1. Furthermore, if it says 2-isopropyl, that's an incorrect name for the 1-methyl ethyl substituent. But you should be able to recognize it, right? Isopropyl is a 1-methyl ethyl substituent. It says 4-hydroxyl, 1, 2, 3, 4. Notice that the alcohols do not take priority whenever you have carbonyls. Furthermore, there is no alkene here. So we did this just to practice the structure and the nomenclature. But in any case, because there are 2 chiral centers here, we can assume that there will be optical activity, although it does not react with the reagent described in the short passage. Which means that 2 will show optical activity, which means we can cross it out because we're looking for the answers or the options that provide you an optically inactive compound after reacting with osmium tetroxide. 3 says 3 says cyclohexene, which is so in the short passage, we're told that this is going to act to give the 2 carbons that contain the unsaturated pi bond, clearly, or that's a redundant way to describe it, but if it's unsaturated, well, not really. If it's unsaturated, it could be a ring or a pi bond. In any case, we're told that osmium tetroxide adds across the alkene to give you 2 syn hydroxyls, which means that upon doing so, you end up with a meso compound, which, as you may remember, is compounds that have chiral centers but that are symmetrical and as a result achiral. There's only two types of molecules, chiral molecules and achiral molecules, or what I like to call not chiral molecules, right? Because if I say achiral, it sounds like a chiral. But in any case, if it's achiral, one property that it's going to have, or I should say if it's not chiral, is that across the board, it's going to be optically inactive. And there's two types. You have those that are meso compounds, which have chiral centers, and you also have those compounds which are lack a chiral center. These are the only types of achiral molecules that you're going to have. And so it's important to know this and then be able to know all the different descriptions that are characteristic of achiral molecules. And as mentioned before, there's only two types of molecules, chiral molecules and achiral molecules. If it's chiral, then it's going to have an asymmetric center, or it's going to have a chiral center or a stereogenic center. They're all one and the same. And there's also a possibility with alkenes that, although not tetrahedral, are able to be categorized as chiral molecules, although those are not likely to show up on these types of exams. But for accuracy's sake, right, we'll just say chiral molecules have stereogenic chiral centers, which means that they're sp3 hybridized and connected to 4 different substituents. If they're achiral, then that means that they do not have a chiral center, or that they do, but they have 2 of them and the compound is symmetrical. Such is the case for Roman numeral 3, which means that 3 will be optically inactive, although it is a chiral molecule. So 1 and 3 are so far the answer. If we look at statement 4, which says fibromose cyclohex 3-ene-1-one, there is an alkene there, which means that it does react with the osmium tetroxide, possibly. 1, 2, 3. Although perhaps less reactive based on the fact that it's a beta conjugated ketone, which basically in short means that there's resonance here, and so probably less likely to react as opposed to cyclohexene that is absent of a ketone. And so the other part of this is the bromine. Notice that there's a chiral center there that has nothing to do with the reaction, which means that this will show optical activity before and after. So 4 will not be included. 5 says you have a methyl group on carbon 1, and on carbon 4 you also have a methyl group. Notice that Me and CH3, and even the absence of CH3 would indicate a methyl group. So make sure you know that although it would appear that Me and CH3 are different things, they're actually one and the same way to describe, or I should say 2 different ways to describe the same thing. Notice that there's 2 alkenes. And notice that this isolated alkene, or diene I should say, because it's 2 alkenes, will not be able to have resonance based on the fact that those 2, or I should say those 2 alkenes are not adjacent to each other with an sp2 carbon in between, right? In order for you to move the pi bond over to any other carbon or substituent, it has to have an MTP orbital in order to accept those 2 electrons. And so in any case, it is going to be reactive. And so as a result, gives you notice that at this point here, you have an achiral molecule based on the fact that this is not a chiral center, right? And so after reacting this with osmium tetroxide, notice that we're told in the passage that it adds it via syn addition, right? Which means it's stereospecific. However, notice that there's two planes to this cycloalkene, which means that there is a possibility in forming a compound that looks like this, although perhaps it's more likely that the compound form actually resembles this opposite configuration, where the alcohols are syn to one another, but on the opposite plane. And so these are stereochemical differences that are worth considering paying attention to, in that with those previous reactions, or I should say reactants in this question, that were able to react with osmium tetroxide were in essence one-dimensional in that they could only give you one possible product. If you have cyclohexene, whether you add it from the top layer of the alkene or the bottom layer, you're going to end up with a meso compound. However, because there are other substituents to account for, as you add the alkene, or I should say as you add the two alcohols, we learned in SN2 and in E2, and even with sterics of any mechanism, that whenever you add something onto an alkene or an alkyne or any compound, steric hindrance is definitely something that accounts to the reaction, in that it's more available on the opposite side of the methyl groups. And so it's more likely that this will be the major product. And so in any case, if we were to assign chirality for these two, how would they differ? Well, if we note the carbons where the methyl groups are at, notice that these are not chiral centers before and after the addition, based on the fact that the substituents are all one and the same. So if we look at this hydroxyl, we can say that this is going to be a chiral center, right? And that you have 1, 2, 3. S being the stereochemistry, or the configuration. For this hydroxyl below on the left, we have 1, 2, 3, giving you R for the configuration. This is an achiral center. For this carbon, we have 1, 2, 3, S for the configuration. And then for this hydroxyl, we have 1, 2, 3, R for the configuration. And so we can see that this molecule is actually going to be symmetrical on two planes, which means it's going to be a meso compound. Now, in the opposite scenario, it's going to be similar in that although there's going to be a difference in the relative stereocenter, where this dashed hydroxyl corresponds to a R for the configuration, we're going to notice that there's going to be a switch for the bottom hydroxyl to S. And for the hydroxyl on the bottom right, it's going to be R. Top right is going to be S. And so as a result, there is still a symmetric molecule that is also a meso compound. Or I should say the former is a characteristic of the latter, right? If it's a meso compound, it has to be symmetrical. But now we can see this also based on the chiral centers. So a meso compound is anything that has 2 chiral centers at least that are equivalent to one another. In this case, we have 4 chiral centers, but that are all opposite to one another. And so all that to review fundamentals, because again, what we're doing here is we're reviewing the fundamentals as we do questions, which I think is more important than doing a lecture first and then doing the questions. So, but sometimes I switch it up. So if you look at question 2, which of the following yields a Z-alkene? Z-alkene corresponds to the stereoisomers, which are going to have an alkene where for both of the carbons have 2 different substituents relative to the sigma bonds, right? So the 2 sigma bonds that an alkene has to have 2 different substituents in order for it to be considered a cis or a trans. Or in proper nomenclature, whenever you have a Z-alkene, that means cis. Remember, Zame, Zi, or cis. Notice that A does not have 2 different substituents for the sigma bonds that lead to the, or I should say for the sigma bonds corresponding to the carbon of the alkene, which means you can eliminate it. B has an alkene, which is already in cis, in the cis configuration. And so here you want to be careful because again, notice that, oh, there it is. There's 3 reductive agents that you have to know outside of carbonyls and sodium borhydride, lithium aluminum hydride, so forth and so on. And that's going to be in the context of the reduction of alkynes. So the important thing to know here is 2 scenarios. If you have an internal alkyne or a terminal alkyne, which is really counterintuitive based on the fact that it should not be called terminal if in nomenclature we actually refer to this carbon as carbon number 1, but that's not up to me. But in any case, just know that a terminal alkyne corresponds to a alkyne with an H on the end. And so if you have one of 3 scenarios, you have to be able to identify the outcome. If you have catalytic reduction, that means you're going to add hydrogens to the point that we cannot say to the point that it's completely saturated based on the fact that you can have a ring within the molecule that is going to end up as a ring regardless of catalytic hydrogenation. Outside the fact that if you have cyclopropane, in this case it is possible, but in the context of alkynes, not likely. If you reduce then this compound so that you have 1, 2, 3, 4, this catalytic hydrogenation is going to keep adding hydrogens until there are no longer any pi bonds within the unsaturated molecule. And so there's another 2 reagents that you have to know. One of them is Lindlar's catalyst. And the purpose of Lindlar's catalyst is to selectively reduce alkynes into alkenes, but more specifically, after it converts into an alkene, it no longer reacts. And in addition, it's stereospecific in that it adds both of the hydrogens syn to one another. Notice that syn is different than cis, right? Because if you have a syn addition, that corresponds to adding the 2 substituents on the same plane. Therefore, we have, this case it wouldn't matter that much, but or actually would, because it leaves you with a cis alkene, which is the whole purpose of using Lindlar's catalyst. With an internal alkyne, will give you a cis alkene. And the other thing to note is you should not just remember that Lindlar's catalyst gives you a cis alkene, because that's not true. That's kind of true, but that's not the entire truth. And that if you have a terminal alkyne with Lindlar's catalyst, then what type of alkene do you get? You don't get cis, you just get an alkene. Because if you have 1, 2, 3, that's actually going to be 1, 2, 3, This would actually be 1. Based on the fact that for nomenclature, we want to give the carbon to the substituent of importance the lowest number possible for the locant. So, in any case, if you reduce an internal alkyne with catalytic hydrogenation, which again is going to correspond to H2 or D2 or T2, right, which are all isotopes of hydrogen, and the metal, be it palladium or platinum or nickel, they're all going to keep adding hydrogens up until there are no longer any pi bonds. And so, in this case, you would end up with a propane, based on the fact that you have 1, 2, 3 carbons. Now, there is another reagent which does the opposite of Lindlar's, and that's the liquid metal reduction. Usually being sodium and NH3L, which means that you're going to add a anti-addition, or I should say add hydrogens anti to one another. So it's going to be a stereospecific reaction, and it's useful in converting alkynes into alkenes, but more specifically transalkenes, if the starting alkyne is an internal alkyne. What would be the case if it's terminal? Notice that if it's terminal, it cannot be cis or trans, because remember, the two substituents pertaining to one of the ends for the carbon that composes the alkene have to be different in order to be categorized as cis or trans. So if you have 2 hydrogens, that's why we said Lindlar's cannot give you a cis alkene even though you have an alkyne, based on the fact that it's terminal. As is the case for the liquid metal reduction. Where you have the same product being formed as if you would have used Lindlar's catalyst. So make sure you know the difference. And the other thing to note is that while it's a common mnemonic to just remember that, oh, Lindlar's catalyst, that gives you cis alkenes, that does not mean that if you have a trans alkene that you're going to make it into a cis alkene if you use Lindlar's, because Lindlar's catalyst, or the sodium and the liquid metal reduction, which gives you transalkenes, those only work with alkynes. They do not work with alkenes. So for the example in B, although you have the liquid metal reductive agent, which gives you transalkenes, you start out with an alkene, which means that there's no reaction, which means that the resulting product will also be a cis alkene based on the fact that that's what the reactant was. So B is true in that it would give you a Z alkene. So read carefully, because it's asking you which one would give you the cis alkene, not necessarily which one will react with the reagent that usually gives you Z alkenes. Okay, C says you have a liquid metal reduction that again will not work with double bonds, right? That only works with triple bonds or alkynes. And notice that C is a transalkene, so therefore it's not going to be an answer. And what would be the result if you use Lindlar's catalyst with that transalkene? There'd be no reaction, right? So remember, the importance of using liquid metal reduction and the Lindlar's catalyst is to selectively reduce an alkyne via a stereospecific reaction that stops adding hydrogens the moment it turns into a alkene. So if you look at answer choice D, which has an alkyne and the liquid metal reduction, that would give you a transalkene, so it cannot be included. And for E, you have an alkyne, which is internal, which means that it has a possibility of being cis or trans, and based on the fact that the reactant is Lindlar's catalyst, it will in fact give you a cis alkene, which means that the answer is going to be 2 of the above. Question 3, which of the following yields a carboxylic acid when treated with 4-methyl pentan 2-ends? So here, we're going to pick up the pace because now we're jumping into carbonyl chemistry from catalytic reductions. If you start out with a ketone, as is the case for this question, and you want to end up with a carboxylic acid, there's only one way that you want to know to do it. Of course, there's many different routes to get to ideal products, but in the context of the reactions that you have to know, the only way to make a carboxylic acid from a ketone would be through the haloform reaction. And so that would correspond to using Cl2, and in combination with a strong base, you know that the ketones have hydrogens which are slightly acidic in that when they are deprotonated, as is the case here with sodium hydroxide or any other strong base, then the heterolytic cleavage that results from taking this hydrogen in this bronzoluric acid reaction gives you a intermediate known as the enolate, where notice that the sigma bond that then converts into a pi bond is going to be established between the carbon of the carbonyl, which already has a full octet, which means that in order to make room for this double bond, you have to move these pi bonding electrons as lone pairs to the oxygen, which gives you a negative charge on the oxygen and an alkene on the carbon. That was a carbonyl carbon as well as the carbon that got deprotonated. This intermediate is what we refer to as the enolate, right? And so it should make sense based on the fact that whenever you have ATE in the context of organic molecules, that's going to correspond to, not always, right? Because it could also refer to esters, but in most cases, if it ends in ATE, think about carboxylate, right? In the context of amino acids or peptides. In any case, that designates a oxygen with a negative charge within an organic compound. And so it should also make sense that it's an enolate based on the fact that it's an alkene. And so it's both a negative charge on the oxygen and an alkene on the same carbon. And so in the presence of this chlorine, you move these non-bonding electrons as lone pairs to establish a pi bond again, that then enables this pi bond between what's the carbonyl carbon and the carbon on the right to turn the pi bond into a sigma bond. So this kind of opens up kind of like a drawbridge, and it picks up one of those chlorines. And so end result ultimately being not an acyl chloride, but a carbon with, instead of 3 methyl or 3 hydrogens, has 1 chlorine and then 2 hydrogens. This process occurs 2 more times, and you should know that each time that there is a deprotonation, it occurs more rapidly, based on the fact that now that you have an electron withdrawing group, the base is able to displace hydrogen more readily, based on the fact that the slightly negative charge that that carbon has for the transient moment in time is stabilized by the electron withdrawing group. So usually, I don't like to go into too much detail for the mechanisms for these types of tests, but these are possible questions. So make sure you know the enolates, and make sure that you know that each successive deprotonation occurs more rapidly based on the presence of electron withdrawing groups. But the end result is ultimately to replace those 3 hydrogens with sigma bonds to chlorine. And so the result, as we learned in ester hydrolysis reactions, is that the hydroxide, instead of acting as a base, in this case is going to act as a nucleophile that adds to the carbonyl and does a nucleophilic addition elimination sequence, then kicking out this carbon with the 3 chlorine groups. Normally carbon is a terrible leaving group, but again, based on the fact that it has the stabilization of these electron withdrawing groups, it's able to do so. So on the actual exam, I recommend you don't write down the mechanism, and I think it is fair to say for certain things you just want to be able to memorize it or recall it, but I think being able to understand the mechanism will help you do those things better nonetheless. So the answer to question 3 has to be E. Question 4, if the starting compound is 3-methyl-4-oxobutanoic acid, determine which reagent would produce a molecule with the following IR data. Broad stretch around 3400 and absorbency in the 2900 region. Now, the 2900 region is the worst place to look at because usually they correspond to CH stretches, which if it's an organic compound, it's probably going to have a CH in there somewhere. The key things you want to look for are broad stretches which correspond to either alcohols or amine groups, in that if you have 2 peaks around the 3200, 3400 region, if there are 2 successive peaks that appear this way, this corresponds to a primary amine. And that, remember, the more to the left that a peak is observed or that an absorbance is apparent in the IR spec, that corresponds to a greater difference in the polarity between the 2 atoms, which is why for alcohols and for NH containing compounds, you see the peaks being absorbed around this region, because there's a big difference in electronegativity when comparing oxygen to hydrogen, hence the big broad stretch. And in the context for hydrogen and nitrogen, there's also a big electronegativity difference, accounting for the 2 peaks in this case, which would correspond to a primary amine. What would it look like if it was a secondary amine? Well, that would dissipate one of these absorbances based on the fact that these peaks appear as a result of differences in polarity, more specifically in regard to nitrogen and hydrogen or oxygen and hydrogen. Hence explaining why if you have a broad stretch at around 3200 to, again, 3500, if you see that, automatically that means that it has to have an alcohol. If it has a peak at around 1700, in addition to the peak around 32 to 3500, then it has to be a carbonyl and a alcohol, which is characteristic of a carboxylic acid, although not necessarily a carboxylic acid, because this could be 3-glyceraldehyde, right? Which would have a carbonyl peak due to the aldehyde and also a hydroxyl. And we'll be talking about this molecule shortly when we look at glycolysis, but make sure that you know that just because you have the broad stretch and the carbonyl peak does not mean that you have a carboxylic acid, although of course that's certainly a possibility. This means that, make sure you pay attention because this is likely a test question, in that they know most students just see a graph like this and automatically has to be carboxylic acid because it's carbonyl and OH. Well, just because you have both of those present doesn't mean that they're connected to the same carbon. So make sure you know that. In any case, there is an absence of the absorbance at around the 1700 region, which is why the answer that we're looking for constitutes the structure of an alcohol or an alcohol-containing compound. And so, based on the fact that you start out with a butanoic acid, and you also have the presence of oxo, which corresponds to the aldehyde, notice that the carboxylic acid takes priority over the aldehyde, hence this being referred to as oxo in the substituent. Furthermore, we have a 3-methyl group, but that's less important. If we look at first option, we have chromate. Any derivative of chromate, be it PCC and pyridium chlorochromate, or potassium chromate, or the only other non-chromate derivative would be potassium permanganate. But those are all oxidative agents in that they convert primary alcohols into carboxylic acids and secondary alcohols into ketones, with the exception of pyridium chlorochromate, which you should know is PCC, in that it's a weak oxidant or a selective oxidant in that it's only able to oxidize once. Notice that that doesn't mean that it always gives you ketones, based on the fact that, or I should say, most students just memorize that, oh, that gives you aldehydes. If you have a primary alcohol and PCC, that would be true. But that's not because you should just memorize, oh, PCC is aldehydes. No, because if you have a secondary alcohol, that would give you a ketone. Key distinction then is knowing that this can only oxidize one time, assuming that it's with a alcohol-containing compound that is able to get oxidized. Because if you have a tertiary alcohol, this would give you a nothing. We're going to learn this in the, in combination of citric acid cycle, and that the reason why you need to convert citrate into isocitrate is based on the fact that you can oxidize a tertiary alcohol. And in the bigger picture or bigger scope of things, the more that you can oxidize a compound, the more energy that can be liberated. And so this explains the importance of, in the Krebs cycle, being able to oxidize the alcohols, right? So we're all over the place here, but we want to amalgamate all these topics together. So they actually, perhaps if a little bit more overwhelming initially, it's going to make more sense that way. So PBr3 is responsible for converting any hydroxyl containing compound into a bromine. So any phosphorus halogen compound is going to have the same effect. So if you have Pi5, the hydroxyl converts into iodine. If you have PCl3, the hydroxyl would convert into a chlorine. And so because you want to end up with a compound that only has alcohols, notice that for A and B, they would not work based on the fact that A would have a carbonyl present, which is not apparent in the question stem, and B would have no alcohol, which means it doesn't work. Notice that NaBH4 is a reductive reagent, and so would give you what when reacted with 4-oxo-3-methylbutanoic acid. NaBH4 adds a hydrogen to the ketone and an aldehyde, and or an acyl chloride, which means that it's not sufficiently strong to reduce the carboxylic acid, which means that the carbonyl would still be present, which is not what we're looking for. Therefore, C would not work. D is talking about ethylene glycol, which we talked about being a protecting group for carbonyls, more specifically aldehydes and ketones, and that ethylene glycol converts the aldehyde into this acetyl group, so that when you add a strong reductive agent, such as lithium aluminum hydride, that is able to reduce both ketones, aldehydes, acyl chlorides, esters. I said both, and then I said like 5 different types, but in any case, the point is lithium aluminum hydride can reduce ketones and aldehydes. if you have a compound that you want to reduce the carboxylic acids, but not the ketones, then you introduce the acetyl group through an alcohol in the presence of an acid that enables this to form. And so if we follow this reaction then, and we treat this with lithium aluminum hydride, which is a strong reductive agent, we know that this is going to convert carboxylic acid into a alcohol. In sequence with the protic workup or the acidic workup, there's two, the purpose of this is going to be twofold. Number one, to establish a bond to a hydrogen, and two, to restore the aldehyde or ketone from the protecting group. Notice in this case, it still has the carbonyl. Therefore, while it's important that you know what ethylene glycol does, it's not the answer to this question. So, D-ball H is perhaps the parallel opposite to PCC in that, whoops. In that it's a selective reductant, the same way that pyridium chlorochromate was, except that with diisopropyl aluminum hydride, you're only going to add one hydrogen. And so as a result, the carboxylic acid, upon reacting with D-ball, would give you an aldehyde. And the aldehyde, upon reacting with D-ball, would give you an alcohol. Which again goes to say that you should not just memorize D-ball gives you aldehydes, although that's generally what it's useful for. It's similar to PCC in that, but opposite in that it has to do with reducing. But it's similar in that it only does so one time. So pyridium chlorochromate oxidizes one time, D-ball reduces one time. Therefore, because we still have a carbonyl present, that means that we can eliminate it. All that to say, and again, when you're taking this on exam, they won't take you this long, but we need to review all these reagents. So if you have an aldehyde, and the same compound as the carboxylic acid, lithium aluminum hydride functions to reduce both groups, more specifically giving you which type of alcohols, primary, secondary, tertiary. Well, if it's a reducing agent that uses hydride, that means that it reduces the number of carbon to oxygen bonds up until it is no longer able to, which will be evident in the absence of carbonyls, right? So that's exactly what happens on this end, which in both cases gives you a primary alcohol. Notice that the difference was that with the aldehyde, you had a nucleophilic addition, and with the carboxylic acid, you had a nucleophilic addition and elimination. You have to be able to identify the types of reactions. You can't just know, oh, this gives you alcohols. You have to know how it does so. So again, for aldehydes and ketones, you know that's nucleophilic addition. Very simple, because prior to having an H there, the only thing you need to ask yourself to distinguish between nucleophilic addition and nucleophilic addition elimination is ask yourself, does the carbonyl pertaining to, or I should say the carbon of the carbonyl, have a leaving group? If it doesn't, nucleophilic addition. If it does, although hydroxide isn't the best leaving group in the world, it's nonetheless able to do so, right? And so this carbon of the carbonyl has a leaving group, therefore it's a nucleophilic addition elimination. That would be the crash course way to understand it. In reality, you should know, though, that upon establishing a sigma bond to a hydrogen, there we go, via a nucleophilic addition, when you establish the tetrahedral intermediate, you again bring this lone pair into a pi bond, kick out the hydroxyl, which then gives you the aldehyde as an intermediate. And so read carefully, because on these types of exams, it's likely that you're going to get a trick question such as, which of the following corresponds to the intermediate for lithium aluminum hydride? And they know that most students just remember, oh, that gives you alcohols. But if they're asking you for the intermediate, you can't just see lithium aluminum hydride and say, oh, alcohol, right? Don't treat this like stimulus response, right? If it's asking for the intermediate, this is actually the intermediate for a reduction of a carboxylic acid with lithium aluminum hydride. And so these are details that are important to not be overlooked, right? So, the last step then is nucleophilic addition. Which is another distinguishing feature too. Lithium aluminum hydride doesn't just do addition elimination. It does a nucleophilic addition, followed by an elimination, and then followed by nucleophilic addition. Based on the fact that in the same way that you have an aldehyde, the intermediate was an aldehyde for the carboxylic acid reduction with lithium aluminum hydride, and as a result, when the aldehyde gets converted into an alcohol, it does so via a nucleophilic addition. Perhaps we're being a little repetitive, but if you do, excuse my French, I very much give a fuck that you do well and that you know all these distinctions. That's why I'm taking the time to go over it. Furthermore, there's one mistake here. I don't know if you caught it, based on how the reaction is written. Well, if it says D3O plus, that is the workup step, meaning the identity of the acid that you add to the hydroxyl will be dependent on which type of workup step you have. If you have an isomer, not an isomer, an isotope of hydrogen, which would be deuterium or tritium, in this case, D3O plus, that means that you protonated with deuterium, which is an isotope of hydrogen, which you should know is same number of protons, different number of neutrons. Notice that hydrogen actually has how many neutrons? 0, right? It has 1 proton, 0 neutrons, which is why deuterium, having 1 proton and 1 neutron, then is considered to be deuterium. And so for tritium, it would be OT, right? And so the actual answer would look like this. Okay. Okay, so question 5, propyl ethanoate treated with which of the following yields a strong absorbance around 3300 cm? What is this really asking you if you distill it to its most simple question? Well, you have propyl ethanoate. Notice that ethanoate, and as mentioned before, not these heuristics don't always apply. So just because I said earlier that if it ends in ATE is going to have, or is likely to have a negative charge, I did also say with exception of esters, right? Which for nomenclature would be propyl, corresponding to whatever carbon group is attached to the alkoxy side of the ester. And the suffix tells you the number of carbons in the longest chain starting from the carbonyl carbon. So if it says propyl ethanoate, we have 1, 2, hence the name ethanoate, right? So make sure that you know that. Don't just assume that, oh, propyl, that should be the longest chain towards the acyl carbon, which is not the case. So, quick crash course on naming esters, right? But in any case, if you react this with KCN, you know that the way to designate a strong nucleophile, or I should say distinguish a strong nucleophile from a weak one, is the presence of a negative charge, with exception of NH3 and any phospho group that's bonded to 3 things. Other than those 2 nucleophiles, which are very strong without having a negative charge, for anything else, be a nucleophilic addition elimination, or SN2, or acid-base reactions, you know that in the context of a base, it's going to be stronger if it has a negative charge. In the context of a nucleophile, it's stronger if it has a negative charge. Notice that Cn with a negative charge by the N is actually misleading, because if we draw the Lewis structure, notice that negative charge actually pertains to the carbon, which is why in the cyano group, carbon acts as the nucleophile. And so perhaps it's been some time since you've seen sophomore organic chemistry, but it is important to note that this occurs as a result of negative moving to whatever is the most positive, as we just talked about in electrochemistry and electrophysics. Opposites attract. For a moment in time, through resonance, notice that this carbon pertaining to the carbonyl is going to have a positive charge. Now, it's more likely that it's going to be in the opposite form. That way, oxygen has a neutral charge, and that way carbon has a full octet in addition to a neutral charge. But in any case, it moves towards this carbonyl carbon through a nucleophilic addition. And what do you anticipate to happen next when you form the tetrahedral intermediate? So there, what you want to do is you want to focus on the fact that it does have a leaving group, and so when you reestablish this pi bond, you kick out this alkoxy group, which means you end up with this cyano group, the carbonyl. Cyano groups are similar to Grignards or any reductive agents in that they continue to add up until there are no longer any pi bonds available. So if you establish another sigma bond there through nucleophilic addition, in this case you don't have a good leaving group, which is why you will form this cyanohydrin, right? Which is whenever you have a carbon bonded to an alcohol and a CN at the same time. Furthermore, the workup step, whenever you have an acidic workup with a cyano group, I'm just going to give you a mnemonic, dare I say, recall and memorize it, right? I know it's unorthodox, but to go over the mechanism would be an improper use of your time, right? Especially for MCAT, DAT, OAT, where it's not all that much into the mechanism. In any case, remember this: whenever you have an acid and whenever you have a cyano group and an acid, you get a carboxylic acid. Whenever you have a cyano group and an acid, you get a carboxylic acid. So it rhymes. That way you remember it. Point being, hydrolyzing the cyano groups with an acid gives you two carboxylates where the carbon of the cyano groups used to be. Furthermore, the only variance is if there is heat in addition to the acid. Remember, way back in Orgo 1, we learned that whenever alcohols are in the presence of an acid, in addition to heat, there's going to be elimination taking place. And also a decarboxylation.